You should have just heard a very nice voice telling you that a recording is now in progress. Very good. So I'm going to go to share screen. I presume everyone can see this okay. This is the winter 21-22 Moon Village Architecture Workshop. You've just heard from myself, Professor Madhu Thangavalu, and Inatani Sensei, the workshop co-chairs. The goals of this meeting are to advance the implementation of the Architecture Working Group studies, to communicate with you and to you updates of the scenarios, the various working group studies, and of OASIS 2045, a space settlement case study, which has been the main focus of architecture working group activities during the past 2 years. We are also going to communicate and coordinate with the Moon Village Evolution team based in Japan that Inatani Sensei leads, and review global concepts and progress toward the moon from various global experts. And we will discuss on day 3 plans for 2022 for the working group. In the invitation flyer that you should have received, you would have seen the detailed objectives of the working group of this workshop. I don't plan to go through these in detail, but just wanted to mention them to you. All of the slides, I am hoping, that are presented will end up available to you. I would like to ask all of the speakers, if you have not yet done so, to please send me by email a copy of your slides. Our themes involve this year, as they did last year, in situ construction and fabrication, in situ resource utilization, life support.
In situ resource utilization.
Correct.
In situ, その場.
Could you please mute your mic? Thank you. Reusable space transportation, power system and operations, and architectural concepts and markets. Give me one moment. There we are. Today's program, I assume everyone can now see the spreadsheet with the program. Madhu, would you do thumbs up if that is true? Can you see it? Yes? No?
Yeah. Yes, John.
Okay, very good. Thank you. So this is this morning's program. There will be an initial keynote, which I'll be giving in a few minutes, providing information on the architecture studies and in particular the status of OASIS 2045. There will be a presentation, series of presentations focusing on construction and manufacturing, beginning with Dr. Raymond Corky Clinton from NASA Marshall, and followed by presentations from Dr. Gao. I apologize if I mangle your name for everyone during the course of these 3 days. we're hoping for a presentation by James Carpenter from ESA, although James has been dealing with some COVID issues in his part of the world, and so we'll see if that happens. And then beginning a little bit later this morning in California, after a short break, we'll discuss in situ resource utilization, and then we'll close. I apologize in advance. Today's closing will be a little bit early. I have to drive somewhere a couple of hours away and get there before noon. And so I hope you'll forgive me. Tomorrow, the program will be a little bit longer. Tomorrow, day 2, we will continue our discussion looking at space transportation and general infrastructure topics, and then continuing with the discussion of energy systems, missions, lunar surface astronomy, and so on. And on day 3, we will discuss some key architectural issues, and we'll have a panel discussion we hope, of the MVA moon market, and then summarize. The day 2 will kick off with a keynote event by Inatani Sensei, presenting the results of the MVA evolution team activities. And day 3 will start with a keynote from Professor Thangavalu with recent results from the USC Space Studio that he runs. And I know I don't have the title quite right here, Madhu. So, but I'll fix it before the minutes. So with that, we'll get started with day 1. Apologize for the slight delay. I hadn't realized when you're recording on Zoom on your own desktop, you are not allowed to minimize the Zoom window. And so as a consequence, I have to sort of guess at where things are on the other side of the Zoom screen. So, okay. Very good. So this is an update of the OASIS 2045 case study. Last year, Professor Thangavalu made a lovely presentation on the vision of the moon and lunar concepts going back well into the last century and the century before that. And I thought I would steal a couple of the graphics that he used in that presentation, in particular to highlight that the earliest visions of humanity traveling to the moon came from the private sector. The one on the left is, of course, Jules Verne in the 19th century. One in the center is later in the 19th century. The one on the right, the two on the right, come from this wonderful, long, silent, black and white movie, Frau im Mond, by Fritz Lang, who also did Metropolis. A central theme in these early visions was the idea that the moon would be reached by the private sector, and that one of the major impetuses for going to the moon would be its resources. As it has turned out, other than the Apollo program and the wonderful landing in 1969 and the later landings and the Cold War competition of that era, the stimulus for much of the interest in the moon now, in fact, comes from lunar resources. These maps show data from the Lunar Reconnaissance Orbiter and other missions, mapping at the South Pole on the right and the North Pole on the left of the moon, the expected presence of lunar ices in the very cold regions found at those locations. I believe in part because of this interest in the moon's resources, and also because of the advent of a wide variety of new technologies since the 1960s, that there is a tremendous effort, international effort now for humanity to go to the moon. That this global consensus is reflected in the diversity of organizations that are participating in the International Space Exploration Coordination Group, from whom we are hoping to hear later in this workshop. I'll just mention this diversity of players, this truly global effort does not in any significant way resemble the race to the moon of the 1960s. I think a similar chart could be made, and perhaps the Moon Village Association could make it, showing not just the space agencies in the ISIC-G, the coordination group, but also the enormous number of companies, private companies and private individuals who are pursuing the vision of humanity expanding presence in its economy to the lunar sphere, to the cislunar space. The Moon Village architecture case study came out of the 2019 Moon Village workshop and symposium in Tokyo and Kyoto, Japan, and the realization that a significant transformation in lunar activities was emerging in large measure because of the advent of very low-cost launch and commercial space activities that were radically reducing the prospective cost of many, many kinds of space systems. The purpose of this case study is to focus on and to define a reference architecture for the first permanent human settlement on the moon. There are, of course, many other activities that are planned on the moon, and some of these may be looked at in the future by the working group, but right now it's on this reference architecture. And that as a part of this case study, there would be the identification of numerous building block systems and technologies, missions and markets, and so on. The reference architecture has been now described and characterized since last year as OASIS 2045, and I'll describe in more detail what it entails in the next slides. The study group logic is as follows. Begin with requirements, the selection of a site for the case study, OASIS 2045, describe the concept, explore the concept of operations, the CONOPS, in the context of missions and markets to be achieved, define and refine the building blocks, and then from that do selected modeling and examine interfaces, interoperability standards, and so on. The starting point, the background for this, of course, was the ISIC-G roadmap from 2020. And we are hoping, as I said, we're going to hopefully hear from the ISIC-G, a representative of the ISIC-G later in this meeting. But also from the 3 scenarios that were framed by the MVA architecture working group several years ago, and the preliminary definition of classes of architectural elements that came from those scenarios. The case study, as mentioned, is looking at a lunar settlement at the south pole of the moon. A series of zones have been identified comprising the lunar south pole, permanently shadowed regions, and volatile deposits in the vicinity of the lunar south pole, the lunar far side, focusing on lunar science, lunar orbit, low lunar orbit, activities in cislunar space, and Earth orbit. A key issue associated with lunar ice and lunar resources is the use of those resources for propellant. And a key driver in all system concepts and concepts of operations, activities on the moon, and on, is the energy required for travel from one point among the 6 zones to another. And so this slide simply highlights the transportation requirements in terms of delta V, change in velocity, from one location to another, including zone 1, zone 2, that's a typo. Sorry, that. See if I can change it. No, I'll change it later. Sorry. That should be zone 1 and zone 2. Zone 3 on the far side of the moon, zone 4 in low lunar orbit, and so on. These delta V numbers, these energy requirements drive much of the analysis that many organizations are doing with regard to lunar activities. Someone is backing up. Okay, thank you. This is a close-up of the region where the OASIS 2045 has been cited during the past year and a half. I'll describe in more detail why that is the case in the coming slides. This is just a close-up of that site, again using data from the Lunar Reconnaissance Orbiter. This is one of the key drivers, the requirement for surface mobility from point to point, and in particular, surface mobility from the location of the targets for ice mining and the OASIS settlement. This is a slope data from the LRO Lunar Orbiter Laser Altimeter LOLA data, which has been invaluable in looking at these topics. And in addition, this is another map of the same region. It highlights the temperatures, the average temperatures in these locations, ranging down in the diamond-shaped PSR at the top of the screen, target number 1 for ice mining, from some 50 degrees Kelvin or so to the crest of the lunar South Polar Ridge, rather, where the OASIS 2045 is anticipated. We're getting quite a bit of air noise, like somebody's walking with their phone. I was just wondering if it might be possible to please mute. Thank you. And this is just the same data set, but highlighting the areas where ice has been tentatively identified. And I wanted to highlight also another factor for consideration by the community, and that is that in the vicinity of the lunar South Polar Ridge, There are a number of locations where there is quite cold. There are quite cold temperatures where it might be possible to exploit those cold temperatures for gas liquefaction, in particular liquid oxygen, liquid hydrogen, to be liquefied, that need to be liquefied for use in to be stored and for use in propellants, and the idea being that the use of natural thermal resources might be a very convenient way to avoid investments in electricity to do the initial refrigeration of such systems, of such materials. So in summary, the drivers for OASIS 2045 and for the selection of the location include the energy environment, the thermal environment, access to material resources, the local surface smoothness, a human factors requirement, in particular, that the settlement should have a view of the Earth, and biological requirements, market requirements, and so on. And here I just summarize the water ice data, the illumination at the south pole of the moon on a particular day, the average temperature data, and the slope data. From these factors, that location, this location here, which we'll discuss more in a few minutes, was chosen. I wanted to highlight one result of studies during the past year, and that is coming off of our meeting last December of 2020. There's a lot of discussion about the subject of ice mining. This is a particular concept that has been looked at by the Colorado School of Mines, by Atkinson and Sowers in a NIAC project more recently. And it involves the idea of essentially using a dome over a section of the lunar regolith to heat and evaporate the ice out of the lunar regolith. The concept that's being looked at, and I have something else I wanted to mention, but I'll get to it right now. The concept that we're looking at in OASIS 2045 is a little different. Given the location of OASIS 2045 here on the ridge, there are in fact several locations that are promising with regard to both temperatures and the presence of ice. One of them was named just a few months ago. Some of you may recall a very fine gentleman and a great champion of lunar exploration and development, Paul Spudis, who passed away prematurely some years ago. Just recently, this diamond-shaped, permanently shadowed region that we had previously chosen as target number one for ice mining because of its convenient proximity in slope and in distance to the OASIS 2045 location, that diamond-shaped, permanently shadowed region has been now designated as the Spudis crater. And I'm calling it here the Spudis PSR. From my perspective, it's an odd-looking thing. It's not a circular crater. It doesn't have an axisymmetric characteristic to it. It looks to me, frankly, like it's been formed by various impactors sort of squeezing in the sides billions of years ago. And so I'm calling it the Spudis PSR rather than the Spudis crater. So please forgive me for the taking the liberty. But it honors a very fine lunar scientist and pioneer. So the new approach to ice mining involves not going to the craters or the PSRs and trying to direct large amounts of energy into them to do the processing of the lunar propellant in 50 degrees Kelvin, but rather to extract the ice-bearing lunar regolith and transport it to the Oasis 2045 for processing. And you'll see in a few moments where those studies have led. This is made possible by the technologies like those that were presented at the December 2020 meeting by Offworld, involving modular robotic systems that could do, and which would be electric vehicles that could be charged and recharged, that would be doing mining in the PSR and then returning the ice-bearing through a series of systems, returning the ice-bearing regolith, for example, starting with the Sputus PSR to Oasis 2045 for processing. This figure just highlights some terrain mapping of these different locations, showing the variations in elevation associated with it. This now zooms in on the, and I want to make sure I don't run over with my time. This now zooms in on the location of Oasis 2045, which is a particular crater about 800 meters in diameter on the slope facing the Earth of the lunar South Polar Ridge. It identifies a location on the far side of the ridge where an initial spaceport might be located. It's about 4 kilometers away from the settlement site, and an impact feature in between the two, which is essentially a small draw along the ridge line, presumably an impact feature from sometime after the formation of the ridge, but it's basically a hole that is accessible by surface mobility, where the temperatures appear not to get above about 100 degrees Kelvin. This looks like a natural cooling site where cryogens could be both produced and kept cold in preparation for use in transportation operations. This is a graphical rendering of the LOLA data mapped onto the lunar surface, showing what these look like, or nominally what these would look like if you had some kind of reasonable illumination everywhere at once. Of course, on the lunar South Pole, you very seldom have anything resembling reasonable illumination. And this just shows a track between the two or the three sites. Most noteworthy, the main line from the Oasis to the spaceport. This curved line, in fact, follows a path of 1,575 meters positive elevation among the above the lunar geodetic mean, with the idea that this would be a convenient path between these locations and one where a lunar road might very reasonably be built that would then represent a connector between these operational sites. Viewing this in another way, this is a conceptual metro map of these locations, showing the primary Oasis 2045 location, this cryogenics depot that I mentioned at this site, the propellant depot, and the spaceport on the far side. It includes these yellow towers, which are intended to reflect solar power harvesters that would then wirelessly transmit energy from one location to another. We had a very good presentation last year from Shinohara Sensei of Kyoto University, and also a discussion from Gary Barnhart. I think both of them are also going to be speaking with us later during this meeting. on these and other topics. Another way to look at the OASIS 2045 is through a functional block diagram. This is a diagram of that sort, and it highlights the interrelationships among the various classes of building blocks that we spoke about a moment ago, that were developed as a result of the earlier scenario-based studies. This is the framework for the definition of other types of modeling and actually cost estimation that I'll describe in just a few moments. In terms of the OASIS 2045, this is an overview of the methodology that's been followed. Begins with the architecture, as I mentioned, the identification of the CONOPS with use cases. The use cases are of critical importance, driven by missions and markets, the resulting definition of system concepts, modeling of those system concepts at the grossest level, i.e. very, very simplistic level, to develop cost estimation relationships, preliminary mapping to the CONOPS. If you need, just as a simple example, if one needs small mining rovers such as this, what is their mass? How many of them do you need? How much energy do they use? And how far do they have to traverse? At what speed? And that's the nature of the modeling that's been done. This is just an example of systems taxonomy within the major categories that came out of the scenarios of a couple of years ago. And it highlights, for example, the lunar ice mining system. So you got in this row item BB142, that's the lunar ice mining system. That would be one of those small robots. And then similarly, all of these reflect a placeholder for some kind of a system to be looked at. Early on, I tried to do a full N by N matrix of OASIS. And one thing I discovered, i.e. with all the interactions among all of the elements, because all of them will interact in some fashion, I discovered almost immediately that this was a bridge too far, too complex to undertake without significant actual funding. However, coming out of a course that Derek Weber and I both lectured at the ISU last summer, I was reminded of the idea of the use cases as a method for extracting data from this fog of future market and system prospects. And that is the approach that I followed since last summer. Derek, I think, is not going to speak this time. Although, Derek, if you changed your mind, please let me know and I'll find a spot for you on the agenda.
Happy just to listen. Thank you very much.
Okay. It was this idea that came out of that joint lecture that Derek and I did last summer at the ISU that reminded me of this methodology of using use cases that I'll describe now. So in particular, taking a slice through the concept of operation for this OASIS 2045 for different missions and markets. 8 use cases have been defined thus far. One involves, obviously, fuel production on the lunar surface. Another one involves spaceport services, then propellant services in lunar orbit from Earth, with the propellant coming from Earth. Another one, lunar or propellant services in lunar orbit with the propellant coming from the moon. The accommodation and travel of lunar visitors, i.e. lunar travel and tourism, but also government-sponsored visitors, a lunar biosphere, lunar power, and lastly, services for a scientific research station on the far side of the moon. These have all been, I'm going to go over these in greater detail during a subsequent talk during this session, during the workshop. But I wanted to highlight that each of the use cases has been framed in terms of a series of specific stages, such as mining, tagging, and storing the ice-laden cold regolith, stage 1.1 in use case 1, and then marching forward until the point where the propellant that has been produced from the water that came from the ice ends up being put into a vehicle for refueling, and the tanker truck returns to its nest. And so I just wanted to give you a feeling for how these use cases work. There's a series of them, as I said, for the spaceport, for propellant services in lunar orbit, for lunar propellant, for Earth-derived propellant. It seems to me this is one of the key trades, and the questions for lunar propellants is how do they compare and contrast lunar source propellants? How do they compare and contrast with Earth-sourced propellants? Lunar visitors, lunar agriculture, in particular, lunar water, power, and transportation services for a human-tended lunar far side station. Just to give you a highlight of one of the items that has been looked at last December, 2020, there was an excellent presentation by Yuzhnoye Space Design Organization in Ukraine, discussing reusable lunar lander and other reusable lunar focused transportation systems that included mass characterization and propellant requirements and so on. Those data on the left-hand side were then used to drive this very high-level modeling that was done to determine how much propellant would be required, how much water to make the propellant, how much electricity to electrolyze the water, and so on, back to the point of determining how much power would be required to produce how much water. Another example, the self-sufficient agricultural system, and I won't go through all of the details on this at the moment, but driven by the idea of a OASIS 2045 settlement of a given size. Not surprisingly, it turns out that the principal driver for energy for a lunar settlement is in fact the especially at the poles of the moon, is in fact the power for illumination of the agricultural region, i.e. plants don't grow without energy, people don't live without plants. In terms of the modeling, used a learning curve approach, manufacturing curve approach, based on some simple cost estimation relationships and estimates of the number of systems to be developed. It's a rather lengthy topic, not one we'll go into in any detail during this week's meeting. If you would like to discuss this in the future, please let me know. We could set up a special meeting to discuss it. This is that lunar ice mining system that I mentioned previously. You can see here in the upper left, very simple model. How big is it? How much is the how much does this robot weigh? how much can it bite, i.e. how much regolith can it move at one time, what is its speed, and so on. And then from that, the development of the concept of operations, and then a determination of its performance over time, how much energy it needs, and so on. And from that, estimate over time with a goal of having a lunar settlement in 2045 with 40 people, the development over time and the deployment over the course of about 12 or 15 years of these lunar mining systems. The idea is based on last year's, or the last workshop, and a challenge from Giuseppe Ribaldi, who's with us this morning, the president of the MVA, a challenge that we shouldn't just say, here's what it might be in 2045, but also how do you get from today to then? And so we begin where the International Space Exploration Coordination Group roadmap ends, approximately. But then we have to think about how would a settlement actually emerge? What would be its growth trajectory? And this is an attempt to begin doing that in economic terms. And just to give you a feeling for how the results turn out, one of the key drivers for power systems to accomplish lunar propellant production, not too surprisingly, is the water content of the regolith, the recoverable water content of the regolith. And the figure on the left just highlights that as regolith content varies from 1 to 7% by mass, the amount of power that's required to do the production of propellant using those lunar ices is a function of that mass content and the number of flights of a reusable lander vehicle that you want to make per month if it is refueled using lunar propellants. And then similarly, you can get a feeling for the cost of the use of the operation of a lunar lander, reusable lunar lander, that is attributable to the cost of electricity on the moon. And so this is the cost per flight due to electricity. Obviously, there are lots of other costs as well. If the cost of electricity is like the cost of electricity on the space station, the International Space Station, i.e. $50 to $100 per kilowatt hour, then for one trip per week, the cost for electricity to make the lunar propellant to fuel the reusable lunar lander is like $20 million per flight up to orbit and back. However, if the cost of electricity is more like cost of terrestrial electricity, i.e. 10 cents to 50 cents US per kilowatt hour, and if you fly more frequently, i.e. maybe once a week, it should be one time per month versus once per week, or several times, 0.25 times a week, then in fact the cost per flight can be significantly lower due to the cost of the electricity. I got a little garbled there and I apologize. The main point there being that the price of the electricity and the utilization of your fixed assets will not surprisingly drive the cost contribution from the power system to the transportation using lunar propellants. A key issue these days, especially in the context of the UN, is that of sustainability, both in future lunar outposts and settlements, and as well as all the other issues. This will be a major consideration. It's not going to be acceptable to spew waste products all over the surface of the moon while we are conducting lunar operations of whatever kind, either mining or propellant production or human habitation or transport. And so all of these need to be taken into account to assure that we have a sustainable lunar future. And this is just a closing statement that a lot of effort has gone in recently to these ConOps, the definition of these use cases. That's going to continue in the future. We'll talk more about future plans for 2022 on day 3. And the goal is to get to a vision of an essentially permanent human activities on our moon, including a settlement such as the Oasis 2045 concept at the South Pole. And I know I've run over just a little bit, and I apologize. I will assert chairman's prerogative, co-chair's prerogative anyway. I've already talked about these themes. We are hoping that there will be a written summary of the workshop, which will be published by the MVA later. If you have not seen it already, there was a written summary from the 2020 workshop that's available on the MVA website. We are hoping to provide copies of presented materials. There will be these recorded videos from the session, and there will be updated planning for the working group going forward from 2021. I wanted to highlight just for a moment one of the issues that we discussed at the workshop in December of 2020 was the need for better coordination among companies and countries and academic organizations, individual NGOs on sustainable lunar activities. At the time, we discussed the need for a global expert group on sustainable lunar activities, GEXLA, as we call it. GEXLA has now been formed and is an ongoing activity. Many organizations are participating in framing a lunar future that will be both global and sustainable. If you would like to get involved in these activities and you're not already, by all means, please reach out through the MVA website. And the leaders for that activity, which include Giuseppe Ribaldi, will get you involved. This was the plan forward a year ago. By Thursday afternoon, we'll be presenting the plan forward for going forward from this discussion. And with that, I will stop a little late. And again, I apologize for being a little late. Wait, I'm not late, I'm early. Ah, good for me. Here I was concerned that I was running over on my time, and it turns out that I'm not actually out of time quite yet. So let me take a moment and ask if there are any questions or discussion based on the material presented before we go on to our first technical speaker of the workshop, Dr. Clinton from NASA. Any questions? Any discussion?
John, thank you very much for a very nice overview early in the morning.
Thank you, Madhu. You and I are in the same time zone, so it's almost 6 a.m. here. So,
that's right,
but not quite yet. Okay. So let me just say, if you do have any questions or you have anything you'd like to raise about this or about other topics during the workshop, by all means, please feel free to ask. And with that, I'm going to turn the podium with a couple of minutes to spare over to Dr. Clinton. Dr. Clinton, if you would be so kind as to briefly introduce yourself to the workshop participants, I will happily present your slides.
Thanks, John, and good morning, everyone. As John said, I work at NASA at the Marshall Space Flight Center. I've been there a little over 38 years now and had a number of jobs in engineering, S&MA, and now science and technology. So interest of mine for the last 20 years has been in-space manufacturing and in-space construction. So we're thrilled to have the project that I'm going to talk to you about this morning. So John, if you could go ahead and load up the charts. I'm going to cut down the video feed just to save bandwidth, and we'll get going.
Okay, very good.
Okay, the project, I'll give you a brief overview this morning, is Moon to Mars Planetary Autonomous Construction Technology, IMPACT for short.
Please go ahead. Corky, we've lost you. Madhu, can you hear me?
I can hear you, but I cannot hear Corky.
Corky, we can't hear you. Perhaps in cutting his video feed. Yeah, he's on mute.
Corky, can you hear us? You could go on chat, perhaps.
Hold on one second. No, we seem to have lost him completely. We'll give him just a moment to rejoin.
John, I think you inadvertently muted everybody for some reason.
No, I didn't try to. I can hear you fine, Dallas.
Yes, I muted myself, but
Okay.
but Corky's muted.
I certainly didn't. I have no idea how to mute everyone, so I'm confident I didn't do it on purpose. Give me just a moment. Well, luckily we were a few moments early.
John, this is Richard. Can you hear me?
Richard, I can hear you, but could you contact Corky and let him know that we can't hear him?
Yes, he knows that. He got kicked off of VPN. He's having to boot it back in, so he'll be on shortly.
Okay, very good. Thank you, Richard. So okay. Dallas, it wasn't my fault.
No, I didn't say it was your fault. It was an inadvertent error.
It could very easily have been my fault. You never know. So please forgive us. We'll pause for just a few moments.
Hey, John, I'm back.
Okay, very good.
Can you hear me?
We can hear you just fine.
Okay, my apologies, everyone. My VPN decided it would cut out. I hope you took the opportunity to go get your next cup of coffee.
It wasn't that long. And now we're just exactly on time.
Okay.
Okay, so back where we were.
And here we are. Yeah, we'll give some more information since we've spent some time trying to scope out the demonstration qualification missions concepts. So that'll be new information. Also want to acknowledge my co-authors, Dr. Jennifer Edmondson, who is our PM, Mike Fisk, Mike Effinger, who are element leads, and Jason Ballard and Evan Jensen, who are our principals at Icon Technology. Next slide, please. Okay, I'm just going to give a brief overview of Artemis simply because I like to trace the work that we're doing back up to the primary program for exploration, and then talk about the Space Technology Mission Directorate, the technologies that they are supporting, including the impact work that is supporting exploration, and that's in the excavation, construction, and outfitting focus area. We'll talk about all those that they have. A brief overview of the project itself, and then getting into some detail on the roadmaps. And then I'll end it up with citing a few challenges and capability gaps that we face. Next chart, please. Okay, this graphic represents the initial series of missions for Artemis. The first uncrewed launch is scheduled for later off this spring of the March-April timeframe. The next mission, Artemis 2, will be crewed, and the crew will orbit the moon in 2024. You might notice that these dates have changed a little bit in the recent months. Initially, we were to have boots on the ground in 2024, and now that's been delayed in Artemis 3 to 2025 to return astronauts to the moon. Artemis 4 then flies to Gateway and continues the development of that outpost orbiting the moon. And then for Artemis 5, there's just an awful lot going there. During this time, there'll be small robotic missions, both science and technology missions like Viper, that's shown on the chart, that will be searching for resources. Cold arm experiment out of JPL that's testing a robot arm and a scoop and doing some geotechnical property characterization of the regolith, and certainly other missions that will come up. Next chart, please. There we go. Thanks, John. This next series of missions will establish the base camp and prepare the way for the sustainable presence on the moon. These capabilities during this series will include mobility systems, both pressurized and unpressurized, power for these capabilities in terms of fission surface power that's being developed, the ISRU power plant for production of consumables, both water and oxygen and rocket propellant, and the foundational surface hab that will be launched from Earth. It's a deployable. Also during the same time, we'll be doing construction technology demonstration qualification missions to create the lunar infrastructure. And that infrastructure will include things like landing pads, roads, foundations, blast shields, habitats, and shelters. Let's go ahead to the next chart, please, John. Okay, now we're moving to STMD, and this represents a broad brush and a top-level view of the organizations of the thrust areas that STMD is funding to support exploration. And there are 4 different thrust areas: go, land, live, and explore. Go is focusing on space transportation. Land is focusing on precision landing for science missions and heavy payloads, providing extreme access to the lunar surface. Live is represented by the focus areas under the Lunar Surface Innovation Initiative, and that's shown in the blue there. And that includes sustainable power, in situ resource utilization, survival in extreme environments, excavation, construction, and not shown on the chart is outfitting. That's new. It was added almost a year ago. And then advanced robotics and autonomy. Also in this suite of focal areas is included dust mitigation. And then finally, there's explore. Those are the technologies that are needed to live, work, and explore on the moon. Let's go ahead and go to the next chart, please, John. Okay, the first thing we have to do, both to understand the engineering decisions on the hardware that we have to build or to decide what is the infrastructure that we need. We believe that the early needs will be primarily horizontal type structures like landing pads, foundations, roads, then moving into somewhat of the vertical scale with blast shields, habitats, and things like greenhouses and whatever support that the ISRU or the power plant may need. So those are our starting points for helping us to scope the size and the capabilities for the construction systems. Let's go to the next chart, please, John. Okay, first, for everything we're going to be doing on the moon, construction-wise and consumable-wise, we'll be starting with excavation. That is a critical portion in order for us to be able to proceed into the more complex problems. We need excavation on the construction side for construction feedstock, materials, site preparation, and conveyance of those materials. So that we can process those into binders or work on them directly without the presence of binders. Now, the lunar environment is a tough environment both for equipment and for astronauts. One of those issues is reduced gravity, which causes a problem for excavators with reduced reaction forces. So the Razor, which is shown there in the center, that's a prototype excavator, has addressed that with counter-rotating drums. Next, you can see in the right-hand photo of that a more industrial scale excavator that we'll need as we scale up to the really industrial levels that we'll need for both construction and for creation of the consumables that we'll need for a sustainable presence on the Earth. And we'll talk about that at the end of the presentation when we get to the challenges. But for now, let's go to the next chart, John. The excavators have to operate in the presence of the lunar dust, and that's a tremendous challenge for them in terms of maintenance and long-term operation. Now let's talk about our impact project. The goal here is to develop and demonstrate on-demand construction capabilities for the infrastructure on the lunar surface using regolith-based materials. And the structures, as we've talked about, are needed to protect the astronauts and also to protect the equipment that we'll have up there from the very extreme lunar environments. And again, we're talking things like we've already talked about: the landing pads, roads, blast shields, habitats, and shelters. We have structured the impact project into 3 elements. The first is impact, and that includes the hardware development and processes, and that development's taking place at both Marshall and also at Icon Technology. The feedstock materials development and microwave structure construction capability. Our objectives are pretty basic. First, we have to develop and demonstrate the construction process and the associated material. Next, we have to develop or adapt instrumentation for in-process monitoring and control, and also the use of the instrumentation for verification and validation of the resulting material. Third, we want to test and evaluate the material on the surface of the moon to make sure that it is sufficient for its operational environment. And then fourth, and this is very important for us, we need to validate that the Earth-based regolith simulant and the simulated lunar environment that we have used for both the material and the environment have been sufficient analogs to enable us to operate or to translate that operation of material to the surface of the moon. Let's go to the next chart, please, John. Okay, this is our structure, and here are our partners. I'm the principal investigator. Dr. Jennifer Edmondson is our project manager and also leading the construction feedstock materials development element. We have a new chief engineer fresh off the success of IXPE, our small astrophysics explorer mission. It's an X-ray mission, and Ron has a wealth of flight hardware development experience. And then our lead systems engineer, Furman Thompson. Looking at the 3 elements for the construction materials, it's primarily associated with universities heavily leveraging our Marshall cooperative agreements, and also center innovation funds. For Olympus, that's the construction system and also several of the processing technology division. Our primary partner is Icon Technologies out of Austin, Texas. They've brought on Search Plus from the 3D printed Mars Hab Challenge, the Bjarke Ingels Group, internationally recognized architectural group, and both Search and Big did some early architectural concepts for us, working on landing pads and habitats that would information later be used to make engineering decisions when we're sizing the hardware. They've also brought on Blue Origin. We also have worked directly with Blue Origin under a cooperative agreement, and that activity is focused on the development of requirements and designs for landing pads, and also then the Colorado School of Mines. And as I've shown here, we have a number of cooperative agreements. Just quickly, University of Alabama, Huntsville, University of Mississippi, Drake State, and I know Dr. Sims is on, and we've enjoyed a great relationship with her at Drake State. Santa Galeska, another minority serving university. Clarkson and Penn State University, primarily looking at geopolymers. And Kepler, which is looking at an environmental enclosure that's needed for our cementitious materials. And I'll talk more about that later. On the microwave structure construction capability, Mike Effinger has done a great job there putting together the team, many of whom have experience from NASA's prior intentions to go to the moon and to Mars. So we're very fortunate to have these experts coming back to help us understand and to mature methodologies to produce building materials by microwaving regolith. Next chart, please, John. Okay, for the construction technologies, we're evaluating multiple materials and processes, and those includes cementitious, I've mentioned geopolymers, thermosetting materials, regolith melting, and that is just brute force, heating it up and melting it, and also forming it into shapes, tiles, laser sintering, and microwave sintering. Now, already we have eliminated, and this is for consideration for DM1 only, because we have to down select to more than likely a single material and its associated process for our demonstration mission 1. So we've eliminated 3 of the cementitious materials, and we're carrying on for a down select for the DM1 mission by the middle of the summer. I mentioned earlier the studies that the Bjarke Ingels Group and Search did for us. You can see some of their concepts here. You can see the habitat on the upper right from Bjarke Ingels, on the lower right from Search Plus, and then also a concept of a piece of equipment building a landing pad that's provided by Icon that also came from these architectural studies. Next chart, please, John. We have enough to do on our hands to build a construction system and work with the materials and the robotics and everything that has to be done to get that first demonstration mission on the surface of the moon. And that is our focal area right now. Fortunately for DM1, we really don't have to solve all the problems, nor do we have to deal with all of the rest of these interdependencies. These will be primarily at DM2 and beyond, and there are other STMD projects that are focused on these areas. For DM1, as you'll see in just a minute, for our artist concept of what that system looks like, all of the excavation, all of the site prep, all of the feedstock conveyance will be done on the end of a robot arm. So for simplicity, we really won't have to do an interface per se with an excavator. And we really won't have to store the feedstock. It will all be done in one operation. So that's really what we're looking at here for DM1. We'll also need the COM and NAV protocol, certainly the COM to transmit the data back and for remote operations. But for the rest of these capabilities, we're really looking at DM2 and beyond when the missions become much more complex. And operating for the deck to the lander, you have minimal impacts from dust mitigation. We're starting with remote ops, but we will incorporate autonomy as we move forward, getting help from Langley there, getting help from Goddard on the avionics. Lander specifications, we're working very closely with the commercial landing services out of headquarters and the different companies that have put out their payload users guides. Power is going to be critical for us, but not until we move to the more complex missions, as will be requirements for the structures that we will be printing. Those are yet to come, as will be lander offloading. So for the further out missions, these capabilities need to be successfully developed by other projects that are going on within STMD. Let's go to the next chart, please, John. Okay, this is our construction roadmap. We're currently on the left-hand side in phase 1, developing the technologies for both excavation and also construction. You can see in that circle, second from left, is the concept of the first demonstration proof of concept mission that we'll be doing for the construction process. As we move into phase 2 and mature these technologies, will enable the construction of functional structures like a subscale landing pad. In phase 3, we move to the lunar outpost, and that's shown in the upper right. Here we construct the habitats, and what you can't see off to the left and the right of that picture in the upper right are a solar farm and also a greenhouse. And inside in the blue circle, you see astronauts working inside that habitat. And then finally in phase 4, we move to the lunar settlement, which is where we really have a sustainable presence on the lunar surface, and that's shown in the background on the chart. Next, let's start talking about how we achieve this roadmap. STMD currently has 4 missions for us that are planned. The first demonstration mission is in late 2026, followed by demonstration mission 2 in 2028, qualification mission 1 in 2030, and qualification mission 2 in 2032. So we have developed our goals and objectives to support this planning. Next chart, please, John. Okay, in addition, excuse me, in addition to the proof of concept for the construction system, we also plan to demonstrate remote and autonomous operations, early instrumentation that includes health monitoring, in-process monitoring and control, and provides some level of verification and validation of the printed material and the test articles. At the end of this, we will reach TRL 6 for the process and possibly TRL 6 for the instrumentation. Let's go to the next chart, John. And again, there's a good showing of the architectural concept for the DM1 lander. For DM2, we do plan to come off the lander and have a mobile system. We will have to interface with the excavator for site prep, for feedstock provision and conveyance, and we'll construct a subscale landing pad with a blast shield segment. We plan to utilize in-process monitoring instrumentation and NDE for the printed materials characterization. Most importantly, we need to be able to functionally test the subscale pad with both mechanical and thermal performance and verify the capability prior to full scale, which is our next mission. Next chart, please, John. Okay, in QM3, we scale up to build what we believe with today's discussion would be a full-scale landing pad for the human landing system. That includes a 25-meter radius pad, a 50-meter radius apron with a hardened surface, and a full perimeter blast shield. For a vertical element, and we're starting to get vertical when we start building the blast shields, we plan to build a subscale unpressurized shelter, which would be a subscale unpressurized shelter, but begin to understand any difficulties and challenges we may face with the equipment as we go to a vertical structure that's higher than the blast shield. At this point, we believe the system will be ready for commercialization, and that is a big emphasis for NASA, is moving this to a commercial system. Next chart. I know I'm about out of time. This is our phase 4 qualification mission 2, which means we are ready to construct whatever infrastructure is needed on the surface of the moon. What's shown here is perhaps a different concept than one might envision when you're building a vertical structure. And ICON has demonstrated this. This was a shelter or a garage for a large piece of equipment that they built at Camp Pendleton for the Marine Corps. And the way they built this was to build the sections horizontally and then lift them and stack them together like slices of bread in a loaf, and they call this the print and lift pattern. They'd intended to do this for the Mars analog habitat at Johnson. You can see a picture of that in the lower left-hand side, sort of a dusty red Mars environment. They ran into an overhead crane problem, but they did complete building that analog habitat. Real quickly, I just want to say a couple of words because I know I'm a minute over about outfitting. So if we could go to the next chart and then the next chart real quickly, John. Okay, this is outfitting, that light blue shaded circle. And the best I can tell you about outfitting, because we've struggled with that definition, is it's the capability that you need to turn a house into a home. Clearly, we plan to build a habitat structure, and this is an interior of the Bjarke Ingels torus, but that's what we're going to build. That's the torus. Inside that, you need all those things that you need, again, to turn a house into a home. You need the mechanical, the electrical, the plumbing, ducting, piping. You need workbenches, tables, and chairs. Now, some of that obviously will be launched from Earth, but gee, we certainly don't want to launch tables and workbenches and sleeping platforms and the like from Earth. Would like to be able to take advantage of that precious cargo volume by using the resources that we have on the surface of the moon to create as much of these furnishings and the mechanical and electrical plumbing and the enclosures that we can do so. And also critical here are the inspection technologies for the habitat. Last chart. Just a quick summarization of the challenges we face. Obviously, we have the problem with interfacing with the excavators. Have to be able to make that link, or we cannot build the more complex structures. We have to scale up. And here we're talking for ISRU production, excavation, conveyance, and construction, scaling up to tens to thousands of metric tons of regolith that's transported over many, many, many trips to the ISRU production facility and the construction. We also have to operate for a long time in extreme lunar environments with the dust environment, and the power has to be there when we need it for anything beyond DM1. For the complex and larger structures, we just have to have adequate power, and it becomes mass prohibitive to carry all those batteries with you. So that I believe is the end, and I apologize for running over for 3 minutes, John, but that's our summary and our plans for the demonstration and the qual missions.
Thank you so much, Corky. That was terrific. A very good kickoff to our technical discussions. I believe our and I won't take any questions at this time because we are running just a little bit over because of your IT issues. But you were right on time. Let me ask is Dr. Gao, I apologize for not saying your name correctly. Gao Feng, are you here with us?
Yes, I can hear you.
Okay, very good. Your audio is a little faint. I don't know if you can.
What about now?
Oh, that's much better. That's much better. Thank you. I'm going to turn on share screen so that you can share your screen. So please, the floor is yours. Please introduce yourself before you begin your presentation. Excellent. We can see everything perfectly.
Okay. Hello, everyone. Thanks for your kind introduction. My topic is outlook on the in-situ space manufacturing for lunar-based construction. My name is Gao Feng from China Academy of Space Technology, CAST. The content is included 4 parts. First one, I will introduce the lunar exploration program of China. The second part is in-situ space manufacturing. The third part is recent development in China. The last part is...
We are experiencing some audio issues, Dr. Gao.
Sorry?
We're getting a little bit of echo on your audio. If you could, I don't know, just try to speak a little closer to the microphone, but we can hear you, but there's some echo.
Okay. The last part is promising research directions. Let's move on the first part. Lunar exploration history mission. According to the three-step plan of China's lunar exploration program, orbiting, landing, bringing back, China has successfully carried out 5 exploration missions. China launched Chang'e-1 in 2007 and achieved lunar orbit exploration. We launched Chang'e-2 in 2010 and go to the Sun-Earth L2 point orbit exploration and asteroid flyby exploration. In 2013, Chang'e-3 achieved soft landing and roving. In 2018, Chang'e-4 successfully landed on the far side of the moon and roving. And 2020, Chang'e-5 achieved moon sample return. Through this mission, China had mastered the technology of orbiting, landing, detecting, sampling, and capsulation, launching, docking, and re-entry, and has established deep space network equipped with the ability to launch space rover, which lay a solid foundation for future lunar station construction. Future plan of China's lunar exploration program. China plans to build an international lunar research station with the participation of international partners. The ILRS will be established on the surface of the moon and or in the orbit of the moon, will serve as a comprehensive scientific experiment facilities designed exploration and use of the moon, moon-based observation, fundamental scientific experiment, and technology verification. The ILRS project can be divided into 3 stages, namely reconnaissance, construction, and utilization. The reconnaissance from 2022 to 2025, the construction from 2025 to 2035, and the utilization since 2035. ILRS constant of lunar transportation facilities, long-term sample facility on lunar surface, lunar transportation and operation facilities, lunar scientific facilities, and ground support and application facility. ILRS 1, establishment of command center, basic energy and telecommunication facilities to satisfy the need of the lunar infrastructure, lunar astronomy, operation, and long-term research and exploration. ILRS 2, establishment of lunar research and exploration facilities, such as lunar physics, geologic profiling, lava tube exploration, lunar sample collection. ILRS 3, establishment of lunar in-situ resource utilization technology verification facilities. ILRS 4, verification of the general technology for following exploration, such as lunar biometric experiment, distributed sample collection and return. ILRS 5, establishment of lunar-based astronomy and Earth observation capabilities. The second part is in-situ space manufacturing. Let me first introduce the definition of in-situ space manufacturing technology. The in-situ space manufacturing technology is an extension of existing in-situ resource utilization technology, including all manufacturing activities in outer space. When comparing with traditional manufacturing on ground, utilizing in space technology, the in-suit space manufacturing technology has obviously advantage in production efficiency, time cost, and product performance. This technology will provide important support for IRIS construction so that humans can truly go beyond the Earth to the universe and carry out sustainable space activity. The in-suit space manufacturing technology include 5 paths: automatic space operation and control, collection, transfer, and storage of lunar resource processing and material preparation, space manufacturing and construction, energy obtaining and production. Part 3, recent development in China. CEST casts have accumulated much experience in automatic space operation and controlled by implementing China's lunar exploration program, manned space flight program, and other major national space projects. Example, robotic assembling, packaging, and transferring on lunar surface through metal DOF robot, coordinate in-orbit assembly, and compliant and adaptive controlled by multiple arms and robots. In situation detection of lunar volatiles, Qian Xuesen Laboratory of Casts proposed technologies such as integrated drilling and encapsulation of lunar volatiles have made a breakthrough in efficient extraction of volatile of lunar cell, efficient sample injection, and rapid detection and analysis. In-suit extraction of lunar water ice, Qian Xuesen Laboratory proposed technology such as integrated drilling, encapsulation, and transfer of water ice, and direct heating of ice-containing soil through the concentrating solar energy. In 2014, Qian Xuesen Laboratory proposed the concept of extraterrestrial artificial photosynthesis, which include process of resource extraction and reactant filtering, material transportation, product separation, and collection. The technology is ready to be demonstrated on lunar surface. Qian Xuesen Laboratory has tested particle size, particle shape, microscope crystal phase composition, and thermal properties of lunar cell. Based on that, an experiment batch for laser 3D printing and molding was built up, and samples of lunar cell were produced. Construction of lunar base. Huazhong University of Science and Technology designed a lunar base named Xuanwu and made a construction experiment using simulated lunar cell. Lunar cell energy storage and power generation. This is based on the temperature difference between lunar days and nights. A prototype model was assembled and feasibility tests were carried out by Qian Xuesen Laboratory. The energy storage temperature of the prototype model is greater than 900 Kelvin. Power generation energy density is greater than 3 watt per kilogram. Thermal electrical conversion efficiency is greater than 30%. The last part is promising research direction. The promising research direction include 5 paths. The first is the in-suit water extraction, oxygen, hydrogen, production on lunar surface. Study water as distribution in permanent shadowed area and the lunar cell. Technology such as water as extraction, refining and extracting water as in lunar cell, energy supply, lunar surface oxygen and hydrogen collection and storage should be developed. Second, lunar cell thermoelectric power generation. Thermoelectric power generation by utilizing lunar cell is quite promising. Technologies such as low loss lunar cell heat storage, efficiency conversion of lunar cell thermal energy to electric energy are critical. Third, in situ construction of lunar base, construction and maintaining landing platform, habitat, and other facility are important. Physical and chemical feature of lunar soil, environment condition of typical area on lunar surface, configuration and structure of lunar buildings, producing and assembly modules of lunar buildings are fundamental technologies that should be conquered. Fourth, regenerative fuel cell. Regenerative fuel cell is promising for future manned deep space exploration, high pressure water electrolysis, purification of product water, heat recovery, and utilization are critical technology. Design and construction of engine used for launch on the lunar surface. Additive material manufacturing is critical for the design and construction of engine. Additive manufacturing device must be able to work stable for long term in high vacuum and microgravity environment. The device should be highly intelligent and have the function of self-diagnostic and self-learning. That's all for today. Thank you.
Okay, thank you very much, Mr. Go. That was a very interesting presentation, and I'm sure everyone learned a lot about China's activities with regard to lunar resources and lunar construction. If you would please stop screen sharing.
Okay. Wait a moment. Okay. I stop the share.
Thank you so much. And I believe a few moments ago that our next speaker joined us. So if I may, without further delay, check James Carpenter, are you with us?
Hello, John. Yes, I am here. Hi.
Outstanding, outstanding. Good morning, good afternoon, and of course, from Asia, good evening. James, let me, without ado, since we're just about back on schedule, let me turn it over to you, and you have permission to do screen sharing.
Awesome. Thank you very much. Can you just confirm that you can see my screen?
Give me one moment, please.
Yes, we can, John.
Superb.
Yeah, I'm glad that you can, Madhu, but I want to be able to see it also. So please, James, say a few words of introduction, if you would, James.
Great. Hi. So, my name is James Carpenter. I'm from the Directorate of Human and Robotic Exploration at the European Space Agency. I'm the Moon Utilization Manager, so I'm responsible for defining a program of activities to take place on the surface of the Moon, including scientific activities. And someone called Pat Sims has a live mic.
Yeah, Pat Sims. Pat Sims, could you mute your mic? Pat.
Back out to the reference.
Dr. Sims.
Yes.
Mute your mic.
I'm so sorry.
Right, thank you very much. I'm putting together a program of utilization activities. So by utilization, we mean science, technology demonstration, the things that we're going to do at the lunar surface. So what I'd like to do today is give you an oversight, some visibility on what we have planned at the moment for our future program. So the exploration program in Europe, in ESA, is contained in something called the European Exploration Envelope Program. And this is currently in its second period. A programmatic period in ESA runs for 3 years between what we call a ministerial council meeting, which is when the ministers from the different countries that are involved in ESA get together and decide on the program budget for the next 3 years. The second period of E3P includes a number of elements. So we have cornerstones. So we have cornerstone 1, which is humans in low Earth orbit. Cornerstone 2, which is humans beyond low Earth orbit. Cornerstone 3, which is moon robotic, and cornerstone 4, which is Mars robotic. And this is goes alongside with 2 transversal activities: expert, which is the part which prepares the future program. So that's mission studies and technologies, and SciSpace, which runs the scientific utilization program. And I tell you this just because it will help you to understand a little bit the scope and the context for some of what I'll talk about later in terms of what are things we might do and what are things that we are doing and when we might take decisions. So the moon exploration is really a fairly new thing within ESA. We've been working on studies and technologies for a long time, but it's really in the last couple of years that this is really starting to ramp up within ESA as part of an international endeavor to explore the moon, which of course you're all aware of. And what we want to achieve through our future moon program is to understand how to live and work in the lunar environment, to identify potential resources and understand how we might use them in a responsible way. And this is something that's actually very important to our stakeholders, is this point about responsible custodianship of the resources of the moon and of space more generally. We want to establish moon as a sustained platform for scientific research, create roles for European industry and commercial opportunities for European industry. That's part of the reason we're here, is to support it and help the European industry. We need to build enabling international partnerships for the near and the long term. And I think that's something that the ESA, I think, pretty uniquely has at its heart, in that it's fundamentally built on international cooperation. And so international cooperation always forms a very big part of everything that we do. And to learn lessons and build capabilities from our activities on the moon that we can then take on to exploration of Mars and beyond. In terms of things that utilization, things that we'll be doing, 2 important documents for us are the ESA strategy for science at the moon and the ESA strategy for space resources, which both are available online. You can Google and find them, and they describe a little bit about what we are planning to do in those areas. In last year and this year, we are working on the preparation of a new strategy for human and robotic exploration, which is called Terrae Novae, or New Worlds. That's something which has been a big effort with our member states to define what they want to do, us being an agent of our different member agencies. And within that, to define a new strategy for overall science within the whole human and robotic exploration program at ESA. So with these in mind, we've been defining the different elements of what we might do next. And the first big thing that we're involved with now, as a big development program, which is very much ongoing now, is our contributions to the Orion through the European Service Module and with the Gateway. So you're probably very familiar with the Gateway. On the left-hand side of this image, you see Orion. So the back end of Orion, containing the solar arrays, the propulsion systems, life support systems, is the European Service Module, which is being developed and built in Europe for multiple Orion flights. On the right-hand side, you see the Gateway, and within the Gateway, ESA is responsible for building habitable volume with the international habitat, and also refueling systems for Gateway 2 and communication systems, among other things. So we're very much involved in that. That's a program which is very much up and running and in development now, to prepare those for the Gateway, which will be an orbital outpost in the vicinity of the moon, where crew will go for extended periods of time, and which can also provide a staging post to reach the lunar surface and come back. So now moving down to the surface of the moon, and also it's worth mentioning we're also working on scientific and technology payloads and utilization activities to take place inside the Gateway and outside the Gateway. At the surface of the moon, we are currently developing a number of activities, but I think the biggest one we're involved with is something called Prospect. And Prospect is a package here, which you see on the Russian Lunar 27 mission. Prospect will drill into the subsurface in near polar locations, extract samples which may contain polar ice, other volatiles. We'll deliver those to a chemical laboratory where they'll be heated to extract those volatiles. They'll be analyzed to understand the abundance, composition, origins, and evolution of those things. So that's a combination of science and ISRU preparation. And we're also able to perform some ISRU experiments to look at reduction processes to extract oxygen from those minerals too. And so Prospect is a package that's being developed now for delivery to the moon with Lunar 27 in 2025, but is also the origin of a suite, a family of payloads which are in development now. And so we have a number of these. So the first flight of a Prospect-derived instrument is actually going to be this year, or as a partnership with NASA on their CLIPS program. It's going to go with Astrobotic on the first Astrobotic mission as part of an instrument called the PITMS. And this is just a small mass spectrometer that is in the chemical laboratory of Prospect. And PITMS will not go to a polar location, but will look at the exosphere on the moon, and in particular the way that human activity and the lander activities influence and perturb that natural exosphere. That's followed then, we have in 2024 a cooperation with JAXA, where we'll be providing, again, a similar mass spectrometer as part of a polar exploration rover, looking at ice and other resources in the polar regions. It's part of their LUPEX mission, which is also a cooperation with ISRO in India. And then we have the full Prospect package, including the drilling system, sample handling system, and the full chemical laboratory. And that'll be going on the 2 flights with Lunar 27 with Roscosmos, and also on a delivery with NASA as a partnership on their CLIPS program. And we also have 2 other payloads that we're working on now with international partners, a laser ranging retroreflector to be delivered with NASA as a CLIPS collaboration in 2024 to Rhino Gamma, and an instrument called NILS, or negative ions at the lunar surface, which will look at the charging and ion production at the lunar surface. And we're investigating that as a collaboration with CNSA for the Chang'e 6 sample return mission. And on the right-hand side there, you can see some of the PITMS instrument undergoing testing. And that's now been integrated with the Astrobotic lander and the Moonlight retroreflector, which is currently in development. I think a lot of this ought to be seen within the context of what I think is an international polar exploration campaign that is happening now. And so if we look at Prospect and the different flights of Prospect, the missions that are taking place between Russia and the United States with their multiple missions like Viper and Prime 1 and the Prospect delivery, along with the missions that are planned from China, Japan, ISRO, I think what we have here is a really interesting collection of missions that are very synergistic. What this image shows is the potential abundance of water ice in the polar regions based on surface temperatures. And the light areas are where we have water ice potentially at the surface, and the darker areas where we have it within a meter of the surface. But what we don't know is the abundance, distribution, the accessibility, utility of this water ice as a potential resource. And so what we're going to have in the next decade are multiple missions making comparable measurements going to very different locations in the polar regions. Now, what this should allow us to do is to put together a geological model of where this stuff is, so that we can then have missions that go and really prospect out a deposit of a potential reserve of water ice as a resource, which these early missions will not necessarily give us, but that gives us the knowledge we can do to really do resource prospecting to follow and resource exploration. And so I think that we should look at all of this in the context of this, and it'd be great if we could start to structure as an international community the way that we're doing this, so that we can really pull this information together to understand the resource potential of the poles better. And we have a great opportunity to do that. So moving beyond these early missions, these early opportunities, we're looking to develop a much more comprehensive capability in Europe and in ESA for lunar exploration. And so for that, we're working on, we call the European Large Lunar Lander. So this would be a robotic lander which can deploy different kinds of payloads. So on the left-hand side there, you see a concept we're working on for a cargo delivery, which would support human crewed missions to the surface. And on the right-hand side, a mission that would have deploy scientific payloads, robotic elements to the lunar surface too, with an astronaut scale. And so this would be a lander which would have around 1.5 tons of payload capacity, would be launched on an Ariane 6. And we're aiming to have this flight ready by the end of the decade. And with that in mind, we've been looking at different kinds of mission that we could deploy with this capability, either within this decade or into the 2030s. So we've been looking at robotic missions to explore the poles. We've looked at an astrophysical observatory to observe long-wave radio on the far side, a complete biosciences laboratory, robotic geology mission, but also infrastructure. So a surface charging and communications station, an ISIU pilot plant, the deployment of a universal mobility system that could be used by crew or robotically, and also general logistics supply. And then with a view for things we could do within this decade, we've been working on a number of different payload studies for science and technology payloads that we could also deploy using the EL3 as a capability for deploying those. Most of those as sub-elements of perhaps larger missions. So we have a lot of activity going on, and over the next months, we need to prepare for E3P period 3 and beyond. So we're in period 2 now. And so period 3 will start next year with our next ministerial council meeting happening at the end of this year. So we have a lot of ongoing technical work going on. We have discussions with different stakeholders, with member states and with international partners to prepare the decisions that need to be taken at the end of this year on the future program and the direction that we go. We expect the decision there to focus on the EL3 lander developments, on contributions to Artemis, and the associated science, and including payloads and sample return contributions. We have advanced study and technology development there for potential ESA-led robotic missions too. We're also looking at potential commercial partnerships to allow us to have lunar surface access even before the end of the decade, so in the next few years, through commercial partnerships and potential new opportunities to participate in international partner missions too. So I hope gives you a reasonable summary of where we're at in ESA regarding lunar exploration, what we're working towards, and the decision points that are coming in the next few years. So thanks very much.
Thank you, James. You have finished a little bit early. If you wouldn't mind stopping your screen sharing. So I don't know if you'd be willing to entertain a question or two, if there are any.
I'd be very happy to take questions if there's questions.
So does anyone, would anyone care to ask a question of James? So if I could go ahead and ask one. So I noted that on one of the landers, the large European lander, there was an example of an vertical solar array as a prospective energy solution. As we heard from our colleague, Dr. Go from China, they are putting quite a bit of emphasis in everything that they're doing on the energy to support a wide range of lunar surface activities, primarily, I think, driven by the lunar surface ISRU and lunar surface construction activities associated with a lunar, an ambitious lunar surface concept of operations. And I'm just curious, has ESA given any thought, or are they considering anything related to energy for lunar surface operations?
Absolutely. So I think for lunar exploration, energy is the bottleneck for everything. I mean, so energy drives either your lander designs or it drives your location. It drives everything. So if you don't have a good energy solution, then you're very limited in what you can do. And so energy is always a problem. Now, what we have in Europe is, of course, the way you'd love to do this is using nuclear power. And in Europe, this is not something that's going to happen quickly. So we have activities to look at radioisotope power sources, but there are some challenges associated with that. Some technical, some political, and policy driven too. So we're working on that. We also have activities to look at ways of optimizing the way we use solar power, but also looking at other mechanisms for energy storage and transmission too. So yes, there's a lot of activities going on related to power. I think that it takes some time. It's not going to come very easy to get to the scales you would want for something like a moon village, particularly as things like the nuclear type options are something that we can't think of in the very near future. But I think we have some good solutions coming together that, coupled with the EL3 lander, would allow us to play a substantial role in the energy needs of surface infrastructure on the moon. So, yes.
Okay. We have time for one more question if anybody wanted to pose one.
John,
Yes,
thank you, James, for a great presentation. And this goes for all three presentations so far. Have all of us paid consideration to the environmental impact of activities relating to ISRU and some of the proposed wonderful ideas?
Absolutely, it's a great question. And actually, if you speak to the general public or we talk to policymakers or others, this point about environmental impact is always one of the first things that comes back. And I don't think we're going to, and certainly in Europe, this is something that I think is very close to people's hearts. And so I think it's important to be clear about that. So actually, one of the reasons why in my earliest slide, I talked about an objective being to understand how we can use the resources of the moon responsibly. And so a lot of the investigations that we're looking at carrying out look into both how we can access, trying to understand the utility of resources on the moon and how we might use them, but also trying to investigate the environmental impact that could have so that we can identify the ways that we do this in a responsible way as custodians of this environment for the future, for science and for other things too. So I think, yes, it's a really important thing that, at least in Europe, this is not something we can't talk about resource utilization in space or on the moon without also talking about this at this point on environmental impact.
Yeah.
Thank you, James.
And just to answer from the standpoint of the architecture working group studies, this is absolutely a strong consideration in looking at the concepts of operations for ISRU and for construction. It's how to best contain any I'll say effluence that might result from human activities on the moon. It is now 7 o'clock. We are at this moment precisely on schedule, which is fabulous. Let me just bring up the schedule. So at this point, we're going to take a break, give people a chance to stretch, get a cup of coffee, or in my case, a cup of tea or a beer if you're in Europe or Asia, if you wish, and we will reconvene at 10 minutes after the hour. So thank you very much. Please be sure to mute your mics, and we'll see you back here in 10 minutes. Thank you.
Hello, everyone. I'd like to check and see if everyone is back online, or at least if some of you are back online. Madhu, are you back? Sounds like maybe no. Inatani Sensei, are you back? Also sounds like no. Is anyone back?
I'm
Yes,
back, John.
John.
It's back.
Okay, sounds like a few are now are coming back online. Okay, very good. Well, that makes me feel much better about being behind time by a moment or two myself. So I just wanted to take a moment and remind everyone of the schedule for the remainder of the morning. We're going to have three more, or the remainder of today's session. We're going to have three more technical presentations. Excuse me for blowing my nose. And then we're going to quit a little early. As I mentioned, I have to drive somewhere a couple hours from here for an appointment around noontime, and so I apologize for needing to finish a little early today. Before we get back into the technical presentations, I wanted to highlight something that I went over quite quickly during the opening keynote this morning. In particular, no, not that one, sorry.
Hey, John, is everybody back?
Yes, Madhu, we're back and we're just getting started. In particular, I wanted to go back for a moment to this modeling framework that highlights a variety of prospective classes of systems. These are fairly generic, and I think encompass systems and capabilities, capacities that would be available both in the OASIS 2045 and earlier. And I wanted to go forward to these use cases that are being defined mostly, and I want to highlight this because as the studies proceed during 2022, this is one of the areas in which I anticipate engaging with many of you to better define these use cases and to assess them. One of the interesting topics for conversation several years ago here in the US involved the question of, well, what is the business case for the moon? Why should, if we're going to do public-private partnerships other than government missions, what is the business case for lunar activities? And there were some studies done here in the US on that subject. And to some extent, really the only, I won't say tangible, but tractable solutions to the problem, to answers to the question, seem to involve seem to involve propellants from the moon and lunar tourism. And so these were the principal reasons why people thought we might go back to the moon. So why there should be ambitious lunar activities. And so I wanted to highlight a little bit more, speak a little bit more about these use cases. And thank you, Dallas, for catching a glitch in one of them. I fixed it before I brought it back up. So at this time, the 8 use cases are basically, they reflect 8 markets or 8 business areas in which there might be lunar activities that would in some way be motivators or missions that a lunar settlement 2045, Oasis 2045, might be engaged in. And the idea in part was to broaden this from simply looking at fuel production and lunar tourism. And so this is intended to better define and refine what use cases, what business models might be viable. As I mentioned, the first and foremost one was the idea of surface propellant for reusable lunar lander operations. And we'll be speaking more about ISRU and about propellants and so on in the coming talks, and about transportation systems tomorrow. Also, as a service, I included a shuttle bus. So one of the things that has to be done that involves spaceport services is to provide transportation to and from the spaceport and the to and from the spaceport and the Oasis settlement itself in several stages. The idea of propellant in lunar orbit, which might be from one of 2 sources, and this is with the intention of exploring the question of where and when do lunar-derived, lunar-sourced propellants make sense in a cislunar economy, which I think is a rather significant question for lunar development advocates. And as you can see, there are a number of stages required, beginning with the ice-laden regolith and progressing through the production of water, the transfer of the water, and in this case, I will just mention one of the elements of this concept of operations, this use case, is to presume that if your goal is fuel in lunar orbit, that you probably don't turn lunar water into LOX hydrogen on the lunar surface, i.e. that you would launch it to low lunar orbit as water and then convert it into propellants on orbit. And so I would welcome comments and discussion about that as we go forward, both during the next couple of days and in the future. And then once you've converted it into water, into oxygen and hydrogen on orbit, then using it to liquefying it to produce the LOX and LH2, do the refueling of vehicles and so on. And alternatively, Earth-derived propellants, and in this case, just to keep everything else equal, again, presuming that for large-scale propellant refueling in low lunar orbit, that probably the thing that you would transfer would be water, and then make the propellants more or less on demand at a refueling station. And so again, I'm very interested in feedback and in thoughts of this ConOps for these two use cases. And then, of course, that's a typo. I apologize. That should be 4. And then, of course, the lunar visitor habitation consumables. And in this case, basically it's trash collection. And this goes very much to the question of sustainable lunar surface presence. This one is not very well fleshed out at the moment, but the basic idea is that you're going to have visitors to the Oasis settlement, Oasis 2045. They will consume air, water, and food. They will produce waste in the form of CO2, water vapor, biological waste, and so on. And that there will need to be some recycling, both chemical, thermal, and biospheric, i.e. through plants and bacteria and ingesters and so on, to then, and I need to, this one needs to be fleshed out a bit, to ultimately end up producing air, water, and food to then subsequently be delivered. And taking large bags of trash and dumping them outside the habitable volume is not a settlement. And then, of course, in order to have biological operations, there's this need for agriculture. The sort of a simple use case model. If you're going to have lunar settlement agriculture of whatever kind, whether it's hydroponics or aquaculture or anything else, is the need to provide from the lunar regolith ice to make water, to grow a lunar habitable volume, to produce and then to deliver the water for the agricultural systems, the things that produce food, and then after the use of the water, recycling and so on, to put that water back into the agricultural loop. And that is a perfectly viable business opportunity. That's the idea of this use case. The delivery of lunar surface power. Here, the presumption is that since this is the goal of the Oasis 2045, is to look at a case study for a settlement. A settlement of 40 people requires something like 20 megawatts or more of electrical power for illumination for the plant growth. Then that involves a very substantial amount of power, not only for the agriculture, but also for the settlement itself, and also for the ISRU, water production operations of all kinds. And so the concept defined thus far is to do that by means of centralized power systems that would then produce and deliver wirelessly power on demand to what are essentially charging stations, i.e. that there would be significant, the concept here is that there would be significant energy storage associated with various Oasis operations, such as electric vehicles and so on, and that the power would be delivered, as I say, on demand. So this is another area to be examined. And lastly, a far side lunar science station that would be human tended. This is being looked at now by a permanent committee of the International astronautical International Academy of Astronautics with an eye towards what are the requirements to assure radio silence in the selected locations on the far side of the moon. The presumption here in this use case is that transportation to and from the far side of the moon for the systems, they would be hauled there in one way or another, but that for people visiting, crew to do repair and maintenance and so on, that they would go by means of a lunar hopper, i.e. a point-to-point lunar surface transportation derived from the reusable lunar lander system, that they would land, and that the hopper then would have sufficient fuel for them to go back after the repair and maintenance operation was completed, and that normally the lunar far side science station would be automated, would be robotically controlled in order to minimize noise and contamination and everything else. So those are the current 8 use cases that are included for consideration. I would welcome any inputs or thoughts from workshop participants. If you'd like to provide those by comments or preferably by email during the meeting or after the meeting, I would welcome your thoughts with regard to additional use cases. Where are there prospective missions and markets for lunar surface activities during the next 25 years, as well as comments or critiques on the specific ConOps, the concepts of operations that are being looked at now. Do you think it would make more sense to make LOX hydrogen on the lunar surface and transport it up to lunar orbit, and so on and so forth?
John, one of the things in looking at your use cases that occurs to me is you have no explicit mention of ancillary services, in terms of communications, time, and navigation. If we're going to have humans there, the expectation will be that it'll be a pervasively networked environment that will have both power and ancillary services readily available
Stop your phone, Gary.
Yes. So that whether or not that constitutes another use case or just another dimension on the others that you have there, that is going to have to be a part of the puzzle.
Yeah, I certainly agree with you fully, and I think the dilemma that I've had thus far is in honing that down to a use case, given that, as you say, it's certainly going to be true that the moon will be ubiquitously networked, and trying to figure out exactly what would be the sort of the end-to-end business model without trying to follow a particular data packet. So
the gambit that in terms of my thinking in this regards, is really treating ancillary services as part of a utility that ends up being provided, which is one model, but
I'm not going to commingle power and data, Jerry.
Well, in the end, actually, you've got to control the power, which means you've got to have ancillary services.
So I understand how you're approaching it as a business, but I'm going to, for the sake of this, for the sake of the work this year, I'm going to treat data as data and power as power.
Okay.
John,
please,
if I may, in the studio that we just had, it was clearly pointed out to me from my students who are in the profession that it's a good idea to pay attention to the US policy of the new administration. And as you know, environment, climate change, and related aspects have come up the ranks to top the list now. And I think it's a good idea to have one case, one use case being climate change and how our activities on the moon can help this whole notion how we can become a cleaner species. Because I think in the long run, space activities have always been a very clean activity. At least we like to think so. So maybe that could be a use case.
Okay, if you're, I will take that on board. If your students had any particular specific ideas.
Oh, I think yes, they did, and one which I think we discussed a little earlier had to do with environment impact. How clean can we operate systems?
Mm-hmm.
And once we show that on the moon, it would have ramifications on Earth. I like to think that.
Understood. May I invite you to cover that a little bit more in your remarks on Thursday?
Oh, well, let me see if we can do that. But I sent you my slides.
Yep.
I'll see if I can do
John,
that.
John, can I just say a couple of words at this point? I owe you some material. We've in our Lunar Commerce and Economics Working Group, we're doing a lot of, parallel activities to what you're doing, and we're developing. We have 9 market sectors, which include things like energy, comms, and navigation, and so on. And we also have been developing what we're calling value chains within each of these market sectors. And to me, they look very like your use cases. Mm-hmm. So we've got some overlap here, and I'm going to send you some material today to perhaps bring you up to speed a bit with what we're doing. And we've got Dallas and Chris on in this 3-day conference anyway, so we can all help you understand what we're doing and the extent to which we can support what you're doing. I just wanted to.
Yeah, that'd be terrific. Thank you, Derek. Okay, let us get back onto our schedule. So next, Dr. Goto from Dohisha University. Are you here?
Yes.
Wonderful.
Yes, I'm here.
So you have permission to share screen. If you would please share your slides.
Okay.
And please say a few words of introduction about yourself.
Okay. Good morning, everyone. I'm glad to have an opportunity to present our research in such beautiful meeting. And I'm Takuya Goto from Kyoto, Japan. I'm professor of Dosha University. Now, I'm also a member of Architecture Working Group in Japan under Inatani Sensei as a material scientist to plan and do experiments ISRU process. Today, I'd like to talk about electrochemical processing for in situ resource utilization. Especially, we focus on electrochemical extraction of silicon from regolith in molten salts. And all results today's presentation beaker scale results will be presented in this presentation. This figure shows Lunar and the surface cross-section of Lunar. The lunar surface contains a resource called regolith. The regolith, as you know, the mixture of various oxide. The variation of the regolith depend on the place on the Mars. And as you can see, this figure, SiO2 silica is one of the most attractive material in the lunar regolith. The amount of SiO2 is also the largest among them, as shown in this table. I will show how to extract silicon containing the regolith. This is an image of the lunar resource utilization. It is a full system that can use the resources of the moon without waste, combined with renewable energies. As you can see, molten salt electrolysis play an important part. So, extraction of extracting silicon and oxygen from regolith in molten salt is one of the key technology for ISRU. And in the future, we aim to build a self-propagation silicon photovoltaic array system. First, we explain future of molten salt. Molten salt is very important in this talk. The molten salt is a liquid salt obtained by heating. And we use molten salt as an extraction media or an electrolyte. The general feature of molten salt is liquid containing only anions and cations. And these features, for example, chemically and physically stable, non-volatile, it means very low vapor pressure. It is very useful for space utilization. Also high electric conductivity and also oxide easily dissolved in the melt. This is another very important point for Xrd utilization. And wide electrochemical window and also high resistivity against radiation damages. And these features deeply depend on the combination of salts such as chlorides, fluoride, and the physical-chemical properties and basicity can be adjusted by the combination of salts. And this figure shows a regolith structure. Regolith contain various metal ions. In this figure, the magnesiums and the iron cation contained in silica network. And you put regolith into a molten salt. You put regolith into the molten salt. This is, for example, molten salt A. The molten salt does not dissolve silica. Silica can be remained as a solid state on the bottom of the beaker, and we can extract by extracting iron cations and magnesium cations. Then we have proposed a new silicon extraction process from regolith silica, and then you remove the molten salt A to this beaker, and you put another molten salt B into the this beaker, then you can do electrolysis to obtain silicon deposition. And to confirm our concept, this is our concept, we conduct the beaker scale experiments. All experiments was carried out in the grow box with furnace, and that kind of cell was this is the electric cell. We use cathode as to collect silicon, and we use also anode as a oxygen gas evolution electrode, and install into the inside here, and we can obtain the silicon by our proposed concept. After silicon was obtained by leaching regolith simulant in the molten salt, we determined electrolysis potential by the cyclic voltammetric data. And this figure shows the cyclic voltam data. You can see the cathodic current correspond to the reduction of silicon cation to form silicon. And then potential static electrolysis at 0.2 volt for 90 minutes was conducted. And this is a XRD and SEM image of the sample after potential static electrolysis. From XRD data, the diffraction peaks coincide with metallic silicon. And we confirmed the silicon deposition on the cathode. And this means that our proposed separation and recovery of metal from regolith can be achieved. We have experimentally confirmed the concept, as I said, silicon recovery from regolith consisting of the following two steps. First, SiO2 extraction from regolith in the molten salt by leaching process, and then electrode deposition process of silicon from silica in molten salts. But the amount of silicon obtained from silica was not sufficient. By calculating from the amount of the electric energy during electrolysis, we realized that design of molten salt bath was very important. So we focus on the electrode deposition process of silicon from SiO2 by electrolysis in high temperature molten salts. In this process, the design of molten salt bath is very important for controlling the characteristic and deposition rate of silicon. And so we investigate the electrochemical behavior and coordination structure of silicon ions in molten salt by electrochemical measurements, high temperature combined with high temperature Raman spectroscopy. This is an experimental setup. Lithium fluoride, potassium fluoride, sodium fluoride melt was used as electrolyte because fluoride melt is known to dissolve oxide very well. And this figure shows the cyclic voltammetry to investigate electrochemical behavior of silicon ion in the melt. After adding 5.0 mole% lithium oxide as oxide sources, broad cathode curve and reduction current was increasing. This figure shows a cross-sectional SEM image of electrode deposition silicon without adding Li2O, the obtained silicon deposition is very thick, about 5 micrometer. On the other hand, adding with 5.0 mole percent Li2O, the thickness of silicon was increased by addition of Li2O. The almost 10 times larger than without Li2O. Also, this is a same image and about EDS and Xrd analysis. The adding with 5.0 mole percent Li2O, the red part is silicon and the green part is silver. As you can see, silicon thickness was changed by applied potentials like this. And this figure shows XRD patterns, and we can obtain the very good silicon at 0.3 volt. And this thickness and current efficiency was promoted after adding Li2O. Li2O means oxide ion sources. We assumed coordination of silicon cation may be drastically changed by adding Li2O. Thus, difference in coordination structure of silicon ion was investigated by using micro-Raman spectroscopy. And this figure shows an experimental setup for micro-Raman spectroscopic measurement. By using this setup, we checked the coordination structure of lithium fluoride, potassium fluoride, sodium fluoride, potassium fluoride, and also we measure the lithium fluoride, potassium fluoride with Li2O or without Li2O at temperature 873 kelvins. This is a result of high temperature Raman spectroscopy. In the case of LiFKF containing SiO2, the Raman band is observed at 1100, corresponding to Si2O52 minus cations, anions. And also, in the case of LiF, NF, KF plus SiO2, also we can observe the same Raman band. And from this observation, we added SiO2 into the such kind of fluoride melt. The dissolution could occur and to produce mainly Si2O52 minus. And after adding Li2O, this case without Li2O, and after adding Li2O, we can observe new peaks as new Raman bands, such as SiO4 minus, Si2O76, and also we newly observed SiO3 F3 minus oxyfluoride anions also observed, and of course we also observed Si2O52 minus, but this band maybe could be smaller after adding Li2O, and fragmentation was promoted by adding Li2O, and the enhance without adding Li2O, the main species Si2O52 minus is rather bigger, but after adding Li2O, the anion is smaller, and this small anion promote to enhance the thickness of silicon deposition and current efficiency. This result shows a component of molten salt were very important, we think. And let me conclude my talk. The electron deposition of silicon from SiO2 in molten salt toward in-situ resource utilization research is current concentration of oxide ion effects on the electron deposition process of silicon in fluoride melts, especially a coordination structure of silicon ion in fluoride melts. And silicon was dissolved by forming SiF and SiO2 bond in molten lithium fluoride, sodium fluoride, potassium fluoride, and lithium fluoride, potassium fluoride at 873 kelvins. And the thickness and current efficiency of polycrystalline silicon layers prepared by potential static electrolysis at 0.2 to 0.4 volt for 1 hour were improved by adding Li2O. And further research should be necessary, such as molten oxide electrolysis, development of inert anode, and also material tailoring under microgravitational environments should be needed. That's all.
Okay, thank you very much. It's a lot to absorb. Thank you so much for sharing your research with us. I'm sure this will these kinds of processes will be of great importance in our future discussions. Would you please stop sharing? Thank you. I apologize, we don't have time for any questions at this moment. May I ask if our next speaker, Michael or Michelle Blanc, are you with us?
Yes, I'm here. Can I share my screen?
If you would be so kind, thank you.
Thank you, Chair. And Michel Blanc is my partner, but today he is not come here, so I will give a talk in place of him.
Very good, thank you.
Yeah, okay. My topic is relevant technology and validation assume patience for ISIU. And here you can see we realized the ISIU is very important to provide the consumable support for human long-term survival and worked on the Lunar over Mars. For Mars, ISIU is more important than the Lunar. And in here, I want to show my great respective and big congratulations to the MOX team, to the JPL, to the NASA. We know in the MVA, now we have international moon days. I think if in the future, we need the ISIU days, I propose use this day for MOX's days for our ISIU days in the future, because we think this experiment is the first on behalf of the humans to realize from the concept to reality, just happened on the Mars. And for the benefit for the ISIU, I have a lot of things I want to see. For prepare the outpost, I think now in the next 10 years, many countries will do these things. They will demonstrate the resource and the proof of the concept of ISIU capability, and they will select the lunar resource, the caricature site for the resource. And for the earlier moon outposts, we will use this to make hydrogens. Maybe they will happen in the south polar area, and we will use it to do the 3D printers for the shield. And for the middle term, the moon and Mars, we will use for the liquid propellant. And for the next long terms, we will use it for the glass products made from the lunar source. And for the recent, the human space flight models, here we give them lunar space flight model here. You know, in the China, now we talk much more about the heavy launch vehicle. The heavy launch vehicle for the cargo delivery is the most important. But what elements influenced the payload's capability of this cargo launch vehicle? I think just because of the this one, and this one, and ISIU. If in the human space flight model, we can let the man-made launch vehicle and the cargo launch vehicle and the spaceship and the cargo and the lunar lander, they are all reusable. We can obviously short the capability of this heavy lunar launch vehicle. And if we can realize the ISIU from the lunar surface, we can also do not need the so big capability of this heavy launch vehicle. Reduce the cost, the transportation cost is obviously have the meaningful for us. And the next, here is ISIU's process. I will give a detailed explanation in the next. For the first step is the resource prospectors. We talk a lot of things about this. This one is in the China, we used the Chang'e 1's microwaves data to make this map. And there, when we joined the small platform of the deep space meeting, we see in the USA, they talk much about the multi-site concept for the Mars. I think this is also for the exploration of lunar or Martian resource. This just is the first step. But if we have, do we have sufficient data to support long-term landing site selection? I think we cannot give the certain answer. Also, in our case study 2045, I still have questions. If this lunar resource, for example, the ice water here, do we know how much they will live there? And this resource assessment, who will do this assessment here? If we selected the source polar site here, how this ice water resource the lifetime? That means how they support us to mining how many years. And I think this site selection and the management is not clear now. And the transportations, lines, convenience is still have these questions. So in the China, we have the Chang'e 6 missions plan. In our plan, we want to exploration the lunar source in the PSR also. But what we really want to know is the content of the ice water in the PSR is how much. And the next is the deployment and the construct of infrastructure here. I think for the sustainable conception is still not clear. I also the member of MVA in the GEGSLA. We talk so much about the sustainable concept, but we still don't know what is exactly meaning of the sustainable. For the PNT, you know, in the Earth, we have 4 systems all around the world to support our communication and navigation. And for the lunar, we have no much so poor and know the network of the communication and the navigation. We need a lot of things to rebuild for the humans survival and for the lunar's industry. So for the deployment of samples, separated transport storage device, and also the emplacement of Habitation infrastructure, we realize that this will have a big difficulty for the humans beings that lived on the lunar. And the next is the sampling separate and the manufacturers. Here is still have a lot of questions for the consumable productions. If all the things we take from the earth to the moons, we cannot support this manner. So we need the ensured oxygen, water, and the food there. And this is just the beginning of the life can survive on the earth. If the peoples on the moons become more and more, we need a lot of resource to support this consuming beings productions. This was a big trouble. And for the next transportation and storage production, they also have these questions. For the excavation and the materials transportations, for in the lunar, we have no roads, no trails, and no airplanes. So the transportations is very is difficult. In the MVA's activity that I attend, I realized that the dust is incentives mechanism, and the dust is do harm to the human and also to the mechanical device. And the next is the cryogens fluid management. I know in the lunar, the temperatures can become dramatically. So how can we contain this currents, oxygen, fluid, and the propellant in there. And the next is autonomous controlled and the futures is recovered. You know, in the China, our first lunar rover U21 is fold on the lunar surface. So I think the false recovers is more important. And the next in the waste disposal and the recycling. In the GEGSLA work group, in my I served for the subgroup 2, and we have 3 tag teams. The tag team 3 is discussing about the lunar environment. We are know in the in situ lunar resource, we have the nature lunar resource, region, mining, metal, wallet, and so on. And here is existing the questions is how can we dispose about ISR use product. For example, we need the water extracted from the PSR in the South Polar. And when we get the water from there, how we dispose of the ISIU waste, especially the lunar reagents. So waste disposal and recycling, we think is very important. We cannot allow the moon or Mars to be polluted like we do on the Earth. So in my group, in my subgroup and Tag Team 3, we want to talk a lot of regulations, rulers for this in time waste disposal and recycling. And next, we have some idea about how to do the technicals verification. You know, in the China, the SIU is at the very beginning stages. People want to know how to use it, but they don't know how to realize it. We know from our sample returned from our Chang'e missions, we know the lunar resource compositions there. So we proposed verifications goes like this. Here we must use based on the small lunar lander platform to do this. If we want to do this, we will expected to arrive at these four goals. The first breakthrough in the critical technology of origin in situ manufacturing based on the lunar soil in the lunar environment. For the human, the origin is necessary, and we think is water we can take from the Earth, but the origin we need more much. And we must have the idea how to produce the in situ. And the next is carry out the flight verification and test the origin product efficiently. We do some experiment on the Earth. We know this is very difficult. If we can expect it up to the 16%, that was perfect. But in realism, experiment, laboratories, environment, even this degree is difficult to realize. And the next is solve the high efficient reactions chamber heating technologies. And the next is provide scientists and technical support for the future human exploration on the lunar or even on the Mars. Here is our plan. Here is the lunar origin generous verifications vehicles. We designed these vehicles. His mass is less than the 300 kg. And for high temperature, you can see here, their electronic, the furnace here, we put this here. And we added the robotic aim, a surface sample device, and to select the lunar soil and separated it by the here is the surface sample arm. And we add a pair of solar area here because, you know, in the Chang'e lunar lander traditional design, they just have one pair here, but this power cannot support to do the ISIU, especially inserted to make the origins there. So we added a new pair of solar area here, and we increased the height area of the cooling plants and add a set of gas composition detections equipment. We want to demonstrate we really can produce the origin, use this verify. So here is the core equipment, the high temperature electrons furnace. This furnace, the mass is not too much. but we must use it to the heating the temperature. It can endure the 200 degrees here. So here is the heating power. We need 500 W here. Here we gave the how to do the lunar surface ozone production process. At the first, we will deploy the solar area here and the cooling pellets equipment ready. And then we will deploy the robotic arm sample regions on the lunar surface. Next, we will transfer the lunar regions and fill with furnace and the sealing the furnace the cover here. And then we will insert to produce the ozone here and separate and storage the gas here. Here is just our imagine of this insert ozone process. But in our laboratory, we really want to do this experiment. Here is our result. You can see here, our experiment is not successful, very repeatable, just because the two questions. We use this furnace and give a high temperature, but the collected the gas from this furnace, the tap was broken. This pipe cannot endure the so high temperature. So because of Lunar's equipment is too simple. This is the first reason. And the next is we cannot separate this different compared this gas from a lot of producing the airs and productings. We cannot separate the ozone from there. So I think our experiment is not reach the goals of our design. It will fail. I think it will fail. But when we clean the product of our laboratory, we found this. This is the semi-analogous lunar regions. Here is one cone in China. We found after this high temperature, the lunar soil becomes a brick, just like this. So we found this was very funny. Maybe we can use the brick to build the lunar moons. So after this result, we communicated and gave our lessons to our international counter partner. And this people is very famous in the China. Here is Robert Rublin's doctor in China. He is very famous. Here is this is mine. This is Robert Julian. We talk about the flight model here, and when he come to our United Custom, we discussing a lot of things of the ISIU, and I translated the two books of ISIU into Chinese. Although my experiment is not arrived successful, we firmly believe ISIU technology will not only change the flight model of human deep space exploration, but also change the life on the lunar or Mars base in the future. So we support to continue to demonstrate ISIU in the next flight missions. Oh, this is what I do in the ISIU and my lessons. I want to share this with you. Thank you for your attention. Many thanks.
Thank you so much. That was a very interesting presentation. It provided us with a lot more detail about the ISIU technology activities and the future plans. Next, we need to hurry along to I'm sorry, Hiroyuki.
Yeah, Muraoka is speaking. Can you hear me?
I can hear you very well. I apologize for.
And are you able to see my pictures?
I'm sorry. We cannot see them yet. Okay, there they are. Thank you so much.
All right, all right. Okay, good morning, good afternoon, and good evening, everyone from Midnight Tokyo. My name is Hiro Muraoka.
Would you please shift to full screen view?
I'm not sure if I'm able to do that in this PDF file.
I think there might be a view and then full screen over on the upper left.
Upper left.
It's all in, of course, Nihongo, so I cannot.
This is maximum that I can make.
No, it's very nice. Please go ahead.
Okay. It is my great pleasure to make presentation at this workshop, and thank you all for giving me this precious opportunity. I would also like to express my special thanks to Professor Inatani, who has been advising TTE since the beginning of our challenge, for inviting TTE in such an honorable event.
John, maybe we should go to the smaller screen.
Yeah,
so
you
we can
should go
see
to
that.
the smaller screen so that we can see the whole slide.
Hello.
Please go ahead and make it a little smaller.
Just going to keep talking.
It is okay?
No, please make it a little smaller.
It's a long day.
Smaller,
Yeah?
smaller, okay.
I went to Natalie.
Alice, I think you have, Alice Miller, I think you have your mic on. Please mute.
Sorry.
How is this?
That is good.
All right.
Very nice. Thank you.
Okay, thank you. Okay, firstly, let me explain who Takasago Thermal Engineering, TTE is. TTE was established in 1923 and will celebrate its 100th anniversary next year. TTE is listed on Tokyo Stock Exchange, annual sales of circa US dollar 2.6 billion last year. Number of employees over 5,900. Our business domain is EPC business in HVAC system. TTE has been a pioneer of HVAC industry in Japan, as shown in the pictures from early last century. On this slide, I would like to explain our hydrogen business. TT has been developing hydrogen technology as a source of efficient energy for the use of HVAC energy resource. We have been making studies on high-performance water electrolyzer at our R&D facilities and brought to the market in 2020. To achieve a carbon neutral world, we plan to develop our EPC and O&M capabilities in this field. On the current model, the H2 production volume is small as 1 to 5 normal cubic meters per hour. But we plan to develop larger scale device to meet the market requirement. Then why space? Our current turnover only comes from HVAC businesses. We are searching for a new long-term business field where we can develop our existing technology. So we chose space as our next field of challenge. So what we do now? We are challenging an ambitious H2 generation mission on the moon. TT has become a HACT-R corporate partner, a program led by iSpace Inc., and also invested to the company for purpose of open innovation. Challenge the world's first demonstrative experiment of hydrogen-oxygen generation in the lunar environment. We will apply the technologies acquired through this mission to both building future lunar economic zone and also solving global environmental issues. Takasago, a non-space company, will become the first penguin which tries this challenging mission and dives into this fascinating space world. Now about the technology. TTE is developing its original solid polymer water electrolyzer system. We have been developing various types of such equipment in the past, and now applying the technologies for smallest and lightest water splitter to meet lunar environment. The mission is scheduled to be launched in 2023 to 24 space mission initiated by iSpace Inc. Now the Japanese government is also supporting us. Ministry of Economy, Trade and Industry appoints this challenging technology under its Stardust program. Stardust program is led by Cabinet Office of Government of Japan, and Stardust stands for Strategic Program for Accelerating Research, Development, and Utilization of Space Technology. So our challenge is now supported by subsidies from Japanese government. The right-hand side chart shows conceptual scheme of water resource utilization system on the moon. The red part, electrolysis process, is just one part of whole system. TTE plans to explore suitable technologies to realize whole system along with the partners who are interested in investigating the technology. From this slide, let me introduce a little bit about Lunar Industry Vision Council, which was formed in July last year. Takasago participated in this Lunar Industry Vision Council, which compiled lunar vision industry towards the Planet 6.0 era. The council is composed of industry, legislators, and academia of Japanese society. Planet 6.0 envisages the Earth and the Moon integrated as one ecosystem with a cyclical social economy. The vision includes 6 declarations by industry and 7 recommendations toward government of Japan. The Lunar Industry Vision advocates the concept of Planet 6.0, which depicts the future vision of the moon from perspective of private sector. The vision proposes measures that Japanese society and industry should take to realize this future. The social benefit of this Planet 6.0 concept would be job creation by means of building a lunar economy and establishing a community on the moon and a world around the moon. The knowledge and experience earned through this new era it would definitely gives back beneficial feedbacks to the issues facing on the planet as well. It was a short presentation from TTE, but this is the end of my presentation. Thank you for your kind attention. Thank you very much.
So thank you very much. That was brief, but extremely interesting. If you would mind to stop sharing.
Okay, hold on, please.
Okay, very good. Yeah, so and fortunately that worked out exactly right because we were running a little bit over time, and now we are almost perfectly back on schedule. So so thank you so much for your help. Before I make some closing remarks concerning today and the preparation for tomorrow, Madhu, would you care to make any comments on today's session?
John, these presentations were very illuminating, and I'm happy to see this last presenter also, and the one before mentioned how we can use our program and this MVA activity on the moon as a mirror to our not only our survival but our flourishing on Earth, because many of these activities we do are clearly a reflection of how we are progressing as a species to become more aware and sensitive to the environment. I think these are a very nice set of presentations today, John.
And Atani Sensei, any closing remark for today?
Yes, thank you for every presenters today, particularly for Japanese presenters, even in the midnight. And anyway, it was a very good talks. Thank you very much.
So, and from my own perspective, I would just say I really enjoyed today's discussion and thought that it was excellent that we had people from the US, from Europe, from China, from Japan. So really a global start to the workshop. Today has focused on overview and manufacturing, construction, ISRU. Tomorrow, we will begin again at 5. We'll have a little introduction, and then the keynote presentation will be in Atani Sensei. And then we will have a series of presentations first that involve transportation and infrastructure with a little bit of ISRU, of course, and then turn our attention to energy and to the idea of an international lunar observatory. So I think it's going to be a very good session tomorrow. I would encourage all of you to attend. And of course, then on Thursday, we will conclude with a very good set of presentations and some further discussion. Let me encourage all of you, if you have not done so, and you are a speaker, to please do send me your slides. And with that, we are just on time. Thank you again to all of the presenters. And I will look forward to seeing you all and seeing the other speakers and so on tomorrow. So thank you very much. We are going to adjourn for the day. Thank you.
Thank you.
Thank you, John.
Thank you.